get started. Work 3's out through the 18th. Final projects should be going. On the final projects, you should have heard from your TF by now. If not, let me know, and I'll make sure that they email you. But I think they've sent out. You did as well, right? You already sent me an email that you had, right? Yeah. So I think all the TFs have contacted you. You should set up a meeting to discuss your project and milestones, make sure they're familiar with it, talk about what you're going to do over the next few weeks and on what schedule. And plan to check in at least once a week, in person, or if you're by email or whatever form, Slack, Carrier Pigeon, if your TF says it's okay. All right, but you should plan on a weekly meeting by default. Make sure to keep you on track, that things are moving forward. If you get stuck on your final project, talk to us earlier rather than later, because when you're scrambling to get things together the day before it's due, we'll make fun of you. 2, we might not be able to help you. We might not have time. So talk to us early about problems, okay? We won't really, no, we'll make fun of you. So the readings. We won't make fun of you for having questions. We'll make fun of you for asking questions so late, just to be clear. It's fine to ask questions. So the readings were look at the matrix multiplication in OpenCL, sort of blog post that went through several iterations of improving matrix multiplication, or the particle simulation in CUDA, which is basically how do you take homework to problem 5 and implement it on a GPU efficiently. There was also a very short article, Efficient Transpose in CUDA, that was very similar to what we did in class on the November 6th, I think. Slightly different approach that got much faster than what we got, and I'll talk about why. And then also mentioned a few people read, which I was quite pleased to see, was this Volkov paper or presentation, just the slides on better performance at lower occupancy, which is a nice sort of paper presentation against the sort of default, the common approaches, common knowledge. So, if you didn't look at the matrix multiplication paper, if you chose to look at particles, that's fine. You might want to go and look at it because it is an excellent example of what a good final project could be and could look like, right? He starts off with something simple. He goes through a bunch of iterations of code, does some analysis on each one. He talks about the idea and why it works and why he thinks it'll work. Some of the things are slower, and that's fine. But his presentation is really good, the way he puts out the work that he's doing and why, and the explanation of how it's beneficial or why you think it will help and how it maps to the hardware. So just, especially if you're doing something that is optimization of an existing technique or some code, where you're going to do several steps of optimization or iteration, this is worth looking at. So he goes through about 10 implementations of matrix multiplication. He does it for general size matrices, where you're multiplying, some m by k matrix, some k by n matrix. And he starts off just with the very naive loop with an accumulator, right? So the purple square in this output matrix is the dot product of the green row and the blue column. And so the initial implementation is just have an accumulator variable. I think ACC calls it. And each thread output, there's going to be a thread per output in the output matrix, just loops over each of the elements in its row and column of the two inputs, multiplies them together, and then accumulates it, and then writes it back. Okay, that's sort of the most basic matrix multiply. Each iteration of the loop goes to global memory for each of these. So it's obviously, there's no optimization there at all. And this is just what he starts to build off of. So his first optimization, as you might expect, is to cache things in local memory, to do some reads into local memory, do the multiplications there, and then go on. Primarily to reduce the number of reads from global memory. And he does this with a tiled multiply scheme, right? He can't necessarily cache enough to load in all the work he's going to do at once, do all the work, and then write out the answer. So they do it in a tiled approach. So if we have one work group that's going to be responsible for the purple square, we need the green rectangle and the blue rectangle, right, to compute that square. Right? Everyone can see that, right? You need the row and the column that your pixel comes from in the output. So that set will need those and those. To make that feasible, so that he can load in enough data for the threads to share, but not overwhelm local memory, he does it with a tiled multiply, where the purple square is the product of the lighter colored squares from the two matrices and the darker colored squares, right? So the output here is the matrix product of this 3 by 3 matrix plus the matrix product of this 3 by 3 matrix. So he's going to load in these two, multiply them together, and store them in an accumulator matrix, and then do the same thing here, and add it to the same accumulator matrix. And so you can see that, you know, for this yellow output, it's this row and column and this row and column. Is this clear? Because he builds off of this from here. It's all going to be tiled after this.
So like I forgot what it's called, but like the work group size would be like 2 times 3 by 3.
The work group size. The work group size in this would be 3.
The work group size, sorry, yeah. The work group size is 3 by 3, but the total amount of memory that like is being used.
The amount of local buffer?
Buffer, yeah.
So the local buffer in this case is just is 2 3 by 3s. Yeah, I think he calls them A sub B sub in his code. Yeah, so he has a local buffer here and a local buffer here. He'll load those up in the usual fashion, multiply them together, and get store in the accumulator, and then load up these and do the same thing. Store in the accumulator, and then after that it's just a write out to the output. And you can see already, since these are going to be read, right, these are going to be copied into local memory, that there's already a big reduction in the amount of reads you have to do from global memory, right? Because you reuse all of these, right? Each column, right, this row is used for all of the outputs here, 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 and here. This row will be used. So instead of going and reading each value that goes into the product of this multiple times, we only read it once for this column. Right, so this is going to be, in this case, it would be something like a 3 times reduction in the amount of global reads. All right, so that's the sort of obvious first step. Use local memory to reduce global reads. And then the next step, which also comes out later in the Volkov presentation, is do more work per thread. Right, in the previous picture, we still have a thread one thread per output value. Right, we're going to tile this with a bunch of threads. They're just going to be in work groups that are going to operate on tiles so that they can share their reads to memory, store them in local memory, store them locally, and then reuse them. They're still going to do that here. But now, one thread is going to be responsible for multiple outputs. And what that allows is there's a lot of extra computation of indices and where is data and what should I read and things like this, which if you repeat it across this whole array, right, if we have a thread per output, the index calculations for this output and the index calculations for this output are very similar. And so repeating them across all these threads, although we have a lot of processors out there, and it's fairly fast, there's still some inefficiency, actually quite a bit. And so what he does next is takes and has one thread responsible for multiple outputs. I forget the tiling terms he uses here. They're various. He breaks it down pretty nicely, though, but he's just going to take and have one thread do multiple outputs so that they can share calculations. All right, and that gets, well, so this is what it looks like. He talks about, okay, let's look at the assembly. And there have been a couple of questions about what assembly is. It's basically the lowest programming language above the actual binary that goes to the hardware. It's things like, load an address. The first one there is load an address memory Load from shared memory a 32-bit float. The second argument is where from, and that's just an address calculation, and stored in this %F50, which is a register name. The point of what he shows you this assembly. So all the C code that we write gets compiled down to assembly, and then the assembly gets assembled into the binary. The point is, when you look at the assembly for kernel number 2, it's in this pattern. Load 2 values from shared memory, multiply them together, and store them in store them in the accumulator. Load 2 values from shared memory, multiply them together, store them in the accumulator, right? And it just keeps going like this. So it's basically 2 reads and a multiply, 2 reads and a multiply. So only 1/3 of our instructions are actually doing work in the sense of doing multiplies, right? We're doing a matrix multiply. 2/3 of our actual instructions are just going to memory. This is in the, in the densest part of the code where it's just multiplying the tiles together. So 1/3 of our instructions are actually doing work, and the rest are just moving data around. So that's in kernel 2. When you do this, where you start sharing the calculations and have multiple outputs per thread, the assembly looks like this. It starts off with some initial setup where it does a couple reads and does a multiply. But then after that, it interleaves. Do a load, do a multiply, do a load, do a multiply, do a load, do a multiply. So now we've gone from 1/3 useful instructions to 50% useful instructions. Still not as good as we could do, but much better, right?
So if you write assemblies like that, can you just put it in a kernel, or how do you put it into your code if you use it?
So if you're going to write assembly like this, what you end up doing is you end up writing something very similar to this code, except instead of naming registers, you'll put in basically some syntax that says use this variable, and it will replace with every variable you have in your code lives in a register. And so it'll replace in the assembly the register that's currently assigned to that variable.
You can do that directly in the kernel?
You can. I don't know how you do it in OpenCL. I don't think you can do it in OpenCL. You can do it in CUDA.
Okay.
I forget how you exactly do it. You can search for, it's called inline assembly. So if you search for inline assembly CUDA, you'll find examples of this. And if you need to do that, it can be quite powerful, but you have to understand very well, what's going on. You would only probably do this in like the most inner loop of your computation, only if you know that there's some sort of pattern of access or registers that you can reuse in a way that the compiler might not be discovering. Okay. It does. Well, it makes it architecture specific. So, assembly, if you write assembly for Intel or AMD or whatever, it's going to be the same. Yes, if you write it in CUDA, but if you're in CUDA, you're already doing something architecture specific. I don't think you can do it in OpenCL, or I don't know how. And yes, in that case, it would only work for the architecture you wrote it for. So if you're doing that, you're already optimizing for a very specific architecture or subset of architectures. All right. His next optimization is not that big a deal. He basically just moves to AVX-like loads. Instead of loading a single float into the register at once, he replaces that with load multiple floats. GPUs have these floats because historically they were used for graphics computations where, for example, you have 3 colors, you have positions in the geometry for rendering an object are represented with 3 values or 4 values. So they already have these AVX-like registers up to 4, sometimes maybe, I think only up to 4 floats in a lot of cases. It doesn't give a real benefit in computation. They're already launching sort of AVX-like multiplies on the compute because of the way that GPUs work in this SIMD fashion. But it is a little bit more efficient for memory loads because it knows that it's adjacent, things like this. So it gives a small benefit. So this is the output for number 3, where he moves to the multiple outputs per thread. And that gives a pretty big boost relative to the first 2. And then a slight increase from doing this load. So larger bars are better. It's basically gigaflops in the kernel. This is the peak from NVIDIA's code for matrix multiply. I forget where, he doesn't show what the sort of theoretical peak is. It's up here somewhere. I think this achieves something like 80 to 85% of what the hardware can do. The absolute, there's a paper, if you chase down some of the references on some of the later pages in this blog post, there are people that do some very in-depth analysis of the hardware and find out that, you know, the best you can do is like 87%. Just the limits on the hardware itself, you can't do better than that ever.
So how come food losses were so much better? They just spent like years optimizing it?
It's written like this.
Oh, God. Okay.
Large parts of CU BLAS are written like this. You know, they went in, they looked at it, they said, okay, how can we condense it down? How can we optimize this? And they optimize for things like register reuse and, you know, interleaving loads and compute. There are a few papers that go into that as well. You can get the Volkov paper or presentation. You can, if you use their methods, you can get up here. I mean, not quite to here, but the stuff that he talks about, you can get up there pretty far. And he shows examples of it. They're not even that complicated. All right, number 5, kernel number 5, he does some transpose, some rectangular tiles, and takes care of brain conflicts. All right, in the same way that we did. Gets a small increase, you know, from 729 to 740 gigaflops. Then optimization number 6 is, okay, let's put more into registers. Registers are faster than shared memory. And optimize some registries, similar to the tricks in the Volkov paper that we'll talk about later in the lecture. It basically doubles the performance with this. Instead of doing local memory, he does some, I don't even remember what he does to force it into registers. But caches more in the registers and does some manipulations there. But this, he says, this is very fragile, and single line changes, you know, minor changes that don't look important in the code will easily drop the performance of this version down to around here. Just like really small changes. So it's not it's tuned, it's well tuned, and will work well on the particular matrix size that he's working with, on the particular hardware that he's working with. But it's a little, you know, unclear that it'll work in all cases. And this one's kind of annoying from an OpenCL perspective. This one is not fragile, was my impression. Like this one, he basically says, okay, well, I'm gonna take one of the previous kernels. I'm gonna take all my OpenCL, pound define my OpenCL to map it to CUDA code, and then compile it with a CUDA. So basically it's a very simple sort of brute force translation of the OpenCL code to CUDA without changing anything else in the algorithm. And it gets a serious boost. So he uses a different compiler. And that doesn't quite get it to here. It gets it to like around here. And then also loads through the texture cache. So I have been lying. Well, I've been lying the whole class. But recently I've been lying about caches and GPUs, right? I've said there are no caches on GPUs. There's no automatic caching. We talked about how the local memory can act as a cache. There's another way you can do caching. It has this texture cache. So GPUs are for doing graphics as well. One of the things they do is texture mapping. Texture mapping is, you know, load an image and then map it onto a triangle or some other shape onto the screen using these coordinates. If you load through the texture cache, if you treat a load from memory, this is a CUDA-only thing, and say, I want to read this as if it were texture, it says two things. One, I'm not going to modify the values, and two, cache it and maybe values around it in the texture cache. Because when you're mapping an image onto the screen, there's a lot of data reuse, there's filtering that goes on. So there's a CUDA-specific instruction that says, use my texture cache, which is not large, but is large enough to provide some caching advantages. Doing that is not the largest increase in performance here. It is worth about 200 gigaflops, but it's still reasonable. And so he basically just says, I'm gonna use a different compiler. I'm gonna do the same algorithm, compile with CUDA and add this one optimization, and suddenly, boom. Right, it jumps from, I think he just uses like one of the earlier kernels and compiles with the CUDA compiler, and suddenly it's much better. Why? Because NVIDIA has spent a lot more time on its compiler on its CUDA compiler than it has on its OpenCL compiler, because they care more about their own market than being portable. Sad but true. And then the last two, he does prefetching and then adds some padding to do arbitrary matrix sizes, which drop his performance. He simplifies, these do not include, these are CUDA and prefetching. The prefetching is basically, instead of having two 3x3 A and B submatrices in the local memory or whatever registers, he has 4, 2 A's, 2 B's. And while he loads in the first A and B and starts to multiply them, but while that multiply is going on, he starts loading the other A and B. So it should be ready by the time the compute is done in the first case. It doesn't work so well. Drops performance, and then he tries to boost it again with some incomplete tiles to allow arbitrary sizes. Both of those do slightly worse. But they're interesting anyway, and they're useful in some cases. Right, so this last one can handle, it doesn't have to be powers of 8, size of 32, but it has a lot of extra calls like padding the matrix and doing these other things. So it's unclear whether, if you had a a matrix that didn't divide by size 8, size 32, and had to pad it for any of these other code, how much is actually due to the padding versus using a different algorithm is unclear. Okay. So it's a nice little walkthrough of here are some optimization techniques, some of which work, some of which don't, some of which are fragile and easy to screw up, some of which are fairly basic and obvious. Nice presentation, especially if someone said, I'm a big fan of matrix multiplies, they're like, me too. All right. The next one, the particle simulation. So if you've installed CUDA, this is one of the examples that comes with it. It's all real time. I don't know what sort of hardware this is on. This is just pulled from YouTube. It's basically doing the same thing that we did in the homework, except in 3D, slightly more complicated physics model, using similar techniques as well, where you have a bunch of balls, you have a regular grid, you store their location in the grid to make it efficient to search for collisions and interactions. It's kind of cool, some of the things. You can see that their physics is more complicated. They have the ability to make things sticky or gravity on or off. These would not be that hard to add to what we did, actually. Their physics model is still fairly simple in terms of the interactions. It's really not, it's maybe 3 times as much or 3 times as many lines of code as we had and a few extra variables per object, but not an insane amount. If you have CUDA installed, it's fun to go and play with this. All right, how do they do it? So I like this, actually. So the uniform grid is my favorite optimization structure, really. It's just like so dead simple. There are a lot of cases where it doesn't even need parameterization. It's basically like the first thing I go to whenever I have some sort of spatial problem to optimize. So these uniform grid, it's all local interactions, fairly simple physics. They have some grid, they have some objects. The first method one that he talks about in the paper but doesn't actually use in the code is we'll just have some amount of storage per grid node, and we'll use atomics to find out where we are. We'll initialize an array to 0, and then when we want to build the grid, we just say, okay, I'll atomically read the value where I should store it and increment that, so the next person that comes along stores in the next location, and then I'll write my ID in here. And then when we need to process the data for a particular node, we just say, okay, well, which particles are here, and when I need to search locally, I can very quickly say, where are my neighbors, right? The same way that we did in problem 5. That's not the technique they actually use because it requires a fixed amount of storage per grid cell, and it's kind of expensive, and a lot of it's wasted memory because there aren't going to be that many objects in a lot of cases. So method 2 is this cool sorting and change point detection. So they start off with, you've got the index of the particle and its cell ID, and then just and then its original, the particle ID. And the first step is, all right, well, let's sort that by where we are, just by the cell ID. In the homework, we use Z order sorting or Morton order sorting. You could use that. It's a trivial drop-in. Right, so now we've got it listed by the cell ID, right? 4, 6, and 9, based on which location they land in the grid. And the next trick is, all right, it's kind of cool. I need to know when I'm processing, when I'm processing these particles, and I need to say, okay, who else is in grid 6? I need to be able to use this index 6 to figure that out. And so to build up this table of locations, they look with a kernel that runs on every particle in this list and says, find where there's a transition from one cell ID to the next cell ID. So where that 4 turns into a 6, where the 6 turns into a 9. And that's a very simple per element check where you just say, okay, I load up this position and I look 1 back, and if that's different than where I am, right? If there's one thread that says, okay, look at this value and look at the value just before it, when it detects a change, that can only happen at one point in the list, right? The change from 4 to 6 can only happen once. And so what it can do is say, well, I see a change, so I will go and write here at 6 that the 6s start at 2. Is that right? And no other thread will do that, right? There's a thread running for each value in this column. But the thread that writes this is the only one that sees a change that transitions to 6. So there's no collisions. Does that make sense? No one's going to write over multiple values here. Is it clear what's going on there? Right, there's a whole column of threads here. And so whenever it sees a transition to a new cell value, it writes where those cells start. And then when I need to do calculations involving cell 6, I just go to say, okay, what particles are in cell 6? Go to 6. Okay, they start at 2. Go to my sorted list at index 2 and walk down until I'm no longer in cell 6, right? So since I sorted by cell ID, they're all contiguous. They start there at index 2. I can quickly do it. And I don't have to have any storage for particle. I don't have to have a fixed amount of storage per grid. I just have this extra cell start list. So much lower memory requirements. So is everyone clear on this? I mean, you don't need to be. It's kind of a nice way to do it if you're going to be dealing with anything physical, but. Sorry?
Would there be an easier way to do it if the particles were on a lattice? Like they couldn't move continually in space?
I mean, if the particles were fixed in space?
Yeah, like they could jump to discrete points in space.
If they weren't floating point positions, but could move.
Right.
Could there be an easier way to do it? I mean, there might be more efficient ways to do it, but in that case, you're imposing something of a grid anyway. So I don't know. I think this technique would still apply, or could be applied efficiently. There were some questions about scattered versus, in the in the write-up for this algorithm, they say, okay, because CUDA can do scattered memory writes and reads, we can do these complex structures. That was not a CUDA-specific thing. He wasn't comparing that to OpenCL or something like that. Any of these, OpenCL can do this as well. It just means non-coalesced reads and writes, where multiple threads within a warp or within a group are reading from arbitrary locations. It'll work. It'll just be slow because they're not coalesced. And he talks about how it might be worth sorting the particles to put them in coherent memory so that when you are doing interactions, for example, with these three particles, if they're near each other in memory, then your reads might be coalesced, or at least be semi-coherent. Someone, I forget who, ran their code and compared to this other code. That was cool. And got roughly the same numbers, right? Our simple 2D multi-core simulation performs about the same in terms of number of particles. The primary benefit for doing it on the GPU is not necessarily performance in terms of compute, but the fact that, you know, talking about the last lecture where the PCIe bus is this tiny little straw compared to the GPU memory and things like that. If you do your simulation on the GPU, you don't have to transfer that geometry or that information across to then render it and show you the thing. So a lot of games do this, you know, where they have realistic physical simulation. They do it on the GPU, not because the GPU is the most efficient place to simulate that, but because then you can draw it very fast without having to transfer a bunch of data across the PCIe bus. All right, and someone else asked about what are gravity or long distance forces. The usual approach in cases like this is something called either fast multipole or Barnes-Hood, or there are various implementations of this, where if all the particles interact with one another, if you have the ability to, especially if the force falls off with distance, which most forces do, or all forces do, then you can do these tricks where to compute the force on the red dot, you look at, you basically glom all these objects that are far away together into a hierarchical structure and compute the force on the red dot based on some sort of combination of everything that lives in the green square. And when you do that, you build this hierarchical structure once per iteration and figure out for each node in the tree that corresponds to this structure, the approximation. It becomes a log n instead of n squared, or n log n instead of n squared operation. And so this was a video, not anymore. If you search for Barnes-Hood on YouTube, you'll find some examples of this. There's, this guy has 3 or 4 implementations of it in JavaScript and stuff. It works pretty well. You can do it on GPUs as well. And people have implemented, plenty of people do this actually. There's a lot of physical simulation for gravitational simulation or electron interactions and all these things that use approximation techniques like this, where there's a hierarchical decomposition of space, and then for things that are far away, you use some sort of approximation instead of the actual n squared algorithm. Now I can't get past it. All right, very briefly on the efficient transpose, right? The main difference here is, again, the amount of work done. They use the same trick that the fast matrix multiply did. I mean, this is our method, right? That we talked about in class. We copy the data out coherently, so the different colors are adjacent threads. The threads read into some sort of local memory. We add 1 to avoid bank conflicts. They write it back coherently. This works pretty well. So the color is basically which thread is doing the work. This is really all that they do. That's the next step up, right? So the first thread is responsible for loading multiple values. I think 4 values each. They do an 8x32 thread or work group and use that to transpose a 32x32 submatrix. So the blue thread reads those 3 values and writes them across. And then when they write back, they do multiple rows as well. So this just shows 1x3 for the work group size. The article is 8x32. And so it should be actually 4 times fewer, not 8 times fewer. but it's basically 4 times fewer index calculations. And that's how it gets so fast. And that's also how the, someone asked, why is there transfer through local memory? They do a transfer through local memory, and it's much faster than the direct transfer. And this is why, right? The transfer still involves index calculations. Also probably some bus contention in terms of writing to memory and reading from it, being a little harder to optimize. Same thing's going on here. By sharing some of the computational work for index calculations, you reduce the amount of basically overhead in terms of load instructions versus move instructions, or index calculations versus memory reads and writes, which are the work that's really going on. Few people read this. It's really kind of interesting, especially if you're in the GPU world. As I've been doing in this class, I've been recommending, all right, run more threads per multiprocessor. That's how we hide latency on the GPU, right? We don't have caches, so we have a lot of threads. When one thread can't do work because it's waiting on memory, if you have a lot of threads resident, you can switch to something else. And run more threads per thread block. This also allows some latency hiding. And then he has like 70 slides showing why this is entirely wrong in a lot of cases. So there are 2 main reasons. Registers have higher throughput than shared memory. Registers are super immediate. Shared memory is like 2 cycles or more. And the schedule limitations require, to make this hardware really use all of its computational power, you basically have to have instruction level parallelism to get peak performance. GPUs have a large number of registers per core, like 128 kilobytes of registers, and up to about 255, which is quite high. I mean, the Intel CPUs have like 3264 per thread, also limited by some number of thread per block. And each little processing unit can host something like 2,000 threads, maximum. But limited then again by how many registers in locality, basically the context size, right? So we talked about this. This is generally the good picture in GPU computation. And it still remains the good one if you've got something that's very computationally intense or that you can't optimize in the ways that he talks about. But the problem is you have limited numbers of threads per registers in this picture. If you've got this, then your context can't be very large, right? If you've got one multiprocessor on the GPU, which usually has around 15 of them, and you've got a lot of threads resident, each one can only have a few registers because you've got so many threads dividing them up. In this case, you don't have the latency hiding from switching between different blocks of threads or different contexts, but you have lots of registers per thread. And so that's what he does. He optimizes for this case. So he uses the registers as a local cache, and he does more work per thread. It's the usual way to take advantage of this. And the important thing to note, and he talks about, is that if you do twice as many outputs in a single thread, that doesn't require twice as many registers because you've got these index calculations that are reused. And so you can get basically more work, you can get denser work onto the GPU. So that's one technique. And then there are also these scheduling limits. This is very hardware specific, and it changes in the next iteration of NVIDIA. It's not super critical to understand, but basically each core is actually on the previous generation. You have 48 threads that are running at any one time on the hardware, and a whole bunch you can switch to. But they're broken up into 3 groups of 16, and the scheduler can actually only do something with 2 of those at a time per clock cycle. So if it can't schedule more than 1 instruction at a time, then you really can't do more than 66 max performance. But we're not doomed. If you have independent instructions, it can actually schedule 2 of them at a time per cycle. So you can basically send 2 instructions to 2 of the, well, you can send 4 instructions in 2 pairs to 2 of the computation engines and keep them all busy. Independent in this case just means no data dependencies. So you see this in regular code as well. But if we're computing x as a plus b, we launch that computation, then we have to wait till it's done before we can use it in this line. But the computation of y can start immediately. So we can, when we're scheduling these 2 instructions, we can basically say do this x equals a plus b, and then do this y equals a plus c. And then when you're ready, then we can schedule this next instruction. But those two can be launched simultaneously, and really in any order. And so that's the instruction level parallelism that he relies on. All right, that's it. Any questions about any of the readings? Great, everything is to, yep. Yeah, I posted on Piazza. So on newer hardware, they have 4 schedulers per core. They also have the warp size is different. All kinds of things change. But this is not as much of a problem there. And NVIDIA does this sort of hot, basically, where is the slowdown in the previous generation? Let's get rid of that in the next one. So the scheduler instruction, or the instruction scheduler, was a problem. It was basically the bandwidth or a bottleneck in the previous iteration in a lot of cases. So they'll boost that, and then they'll find what's, they'll run through the next iteration and figure out where the next bottleneck is and fix that. So next time we'll wrap up OpenCL. Basically, last bits of that, and talk about GPUs. If there are any questions, particularly related to the homework, post on Piazza. We'll have IACS potential students visiting, so come up with good questions so that we can look good. The more esoteric, the better, so that their eyes can just glaze over and their heads explode. Again, talk to your TFs about final projects. Get started on those things. All right. Thank you. See you Friday.